are the
No, it's fine. It's
end of the semester, the moment you've all been waiting for.
Laser.
We have reached the pinnacle of our discussion of waves. There's lots more we could do, of course. We spent a lot of time on really important things and thinking about oscillations and complex convention and so forth. And there's no end to what we could do beyond this. But today we've arrived at chapter 8. There's lots of stuff in chapter 8 relative to waves, traveling waves. There's Doppler effect and so forth. But what I really want to spend today thinking about is interference and diffraction phenomena. You covered this in Physics 2, of course, and I've just posted to Canvas problem set 8 a summary of the phenomena from that point of view. So if you want to take a look at that, you're welcome to do so. Oh, and I didn't bring a diffraction grading down, shoot. But let's, I put on your tables a laser and a couple of slides. And so let's just review this phenomenon real quick. So first of all, laser safety. Because the laser beam tends to be non-diverging, it doesn't carry very much power, but if that went through your eye, it would focus down to a single point and deliver a high intensity to that. These are not very powerful lasers either, but if you stared at the laser, it could burn out some cells in your eye. So never look directly at any laser. Always aim the lasers away from other people and cause them not to fall on people's eyes. Avoid specular reflections like off of mirrors and so forth. But let's go ahead and turn your lasers on. These are cheap lasers you can get from Harbor Freight. Push a little button on it. Then
ricochet off into my eyeball.
Pull up the slide. Well, let's start with the single slit slide. So there's a slide that has 4 examples of single slits. Number of slits 2, number of slits 1. And so why don't you cause the laser beam to fall upon those one at a time. I'll turn the lights out here so we can see it better. You will, the pattern is going to be very small, so it will help if you have a large distance to your screen, whatever screen like the wall you're looking at.
Yeah, William has to move his thing. Oh!
Oh, there we go.
Wow.
There we go,
What's
nice.
that? 1, 2, 3.
Now that's the double slit.
Yeah.
So let's start with a single slit.
That's 7 bright spots. Wow. I was only getting 3.
Oh, there's one.
That's just the me.
Just one.
What is this commentary?
Okay, so you see a pattern. Everyone's got a pattern. All right, describe that pattern to me.
The brightest spot is in the middle, and then bright spots around it that get incrementally less.
Okay, so I hear you saying there are multiple bright spots,
Mm-hmm.
of which the brightest spot is in the middle.
Mm-hmm.
Okay.
Yeah.
We'll give that brightest spot in the middle the name the central maximum. Now, is that spot in the middle, is it a spot? What's the shape of that?
Like an oval.
It's an extended line. Okay. All right, good. And then, so you said there are multiple bright spots, which suggests that there are dark spots. Are there dark spots?
Yeah.
Okay.
Yep.
All right. Notice which is wider, the dark spot or the bright spots?
Bright
The
spot.
bright spot is wider.
Bright spot is wider, right? So the dark spot, which we're going to call it a fringe, historically, So the dark fringes are easier to locate. And so for this pattern, the single slit pattern, we will define the locations of the dark fringes. Can you tell, so you told me that the central maximum was spread out. What about the other less bright spots? Are they spread out or are they points?
They're spread out.
They're kind of
They're
dashes.
spread out as well. Okay, what's the width of those less bright spots, fringes, compared to the central maximum? Are they the same width or different?
About half.
They're less.
Yeah, they get smaller.
Okay, right, good. So if you look on the projection, which of these three patterns looks most like this double slit, the single slit pattern? And here on this, where you see black or red, that's supposed to be bright.
Oh,
So
okay.
the
That
singles.
makes- Yeah. I thought that was dark.
Yeah, I know, well.
Confused. Okay, yeah, that's that.
I didn't have the option of having a black background, so you have to invert it. Thank you. Right, so it's the one labeled single slit diffraction. Now we're going to use the words interference and diffraction, and I know that I was confused about this when I was a freshman. Diffraction refers to the spreading of waves, and so if you drop a pebble in a pond, the wave spreads out in all directions. I rather like to think about Huygens construction. Huygens, a Dutch physicist, H-U-Y, Huygens, who said, if you have some source of light that's spread out, if you have a point source, light, of course, travels in circular or spherical patterns out from that single point source. But if you have an extended source, like in this case, a single slit, we have a plane wave of light falling upon the single slit. And so if this is my slit of width W, single slit, then I can consider that that source, which is of this width W, as composed of a bunch of little point sources spread across that. All right, and you can think of each of those point sources as radiating out spherical waves from that. And if I add all of those up, then I will arrive at something that looks like a flat wavefront in some circumstances, depending on the wavelength and so forth and so on. And so so I can consider a plane wave of light as having been produced by a whole array of sources. And then if that plane wave encounters any obstacle, then I can reconstruct, as it were, from point to point to point on the progression of this wave. I can reconstruct each of those as a new series of point sources on that. Okay. So we were just talking in optics lab yesterday about using this to think about what happens when you have light refracting, going from, say, air into water, and what happens when the light hits the water. Well, again, you can think about when the light hits the water as another bunch of point sources, and consider what happens with the waves that progress from that in a slower velocity. All right, so that's one way of thinking about it. And we're going to do that in our work today as homework. And so again, as we did on Wednesday, whatever we can do in class will constitute our homework for Chapter 8. Okay? All right, so so I was just talking about diffraction, talking about spreading. This is what's happening, right? Each of these point sources is radiating light that's spreading out in all directions. And so although we would get our bright central maximum as the progression of this relatively flat section as it spreads out, we also get stuff spreading out to the sides. If you look at those slides and how big are the slits on those slides? They're very small, right? And yet the pattern is spread out left and right, quite a bit bigger than that slit. So again, this is a sense of diffraction. We're spreading out. Why don't you, the slides are labeled as terms of how big the slit widths are, what the W is on these slits. Why don't you go to a different, you'll notice that the two tables have different patterns. Go to a different width slit and tell me what happens to the pattern.
The dashes got longer.
Aha, okay.
Longer dashes.
And was your new slit wider or narrower than the original?
I'm guessing it's wider. Maybe. I have no clue.
Yeah, it's a little hard to see from over.
Yeah. I don't know. Which one is it?
Oh, there's labels.
I can give you another one if you want to read it.
I'm like at a 90-degree. I'm supposed to be really.
I think it's an issue.
Here, if you want
So we do.
to read that,
Oh, there
So
you
what's
go.
that
Now
one?
you can
So-
do it.
if you want to read
You're
this.
looking at,
So the one over here, what? Is 0.08 millimeters. This one is also 0.08.
Oh, wait, that makes sense, because that means there's less,
so these say 0.02, 0.04, 0.0.
Right, this is the 0.01.
Okay, that's 0.01.
So, okay, and slit
Two.
space
Okay,
goes from 0.5.
0.0, is that 0.04?
Or no, or 0.02, 0.04.
Yeah.
Let me go back and so
Yeah.
I'm taking a video.
Yeah,
This one's the double.
This is 0.02,
Which one is a
0.04,
okay,
single one? This is a single.
0.08,
okay.
and
These are all double. These are all
0.16
double.
0.16, yeah.
Yeah, this is a double.
wow.
Okay.
for single slits.
Oh, this one's a single.
That's a single? Alright, perfect.
Okay,
All right.
so
Okay,
this one is 0.16.
so that's
And this one is
0.16.
0.08 millimeters. So I think we.
So this table over here, their pattern was your slit, is your new slit narrower or wider?
narrow.
If it's the same as this one, it was
Unless-
narrower.
Narrower, okay. So when you made the
Unless-
slit narrower, the pattern got
What's
wider.
that?
What happened over here? Your pattern got narrower,
Yeah,
Unless I have this on the wrong side, you know? If it's supposed to be oriented like
and
this.
so did you get that narrower pattern by going into a narrower slit or to a wider slit?
a wider slit. As we went up to 0.16, ours got narrower, so we're flipping it to C.
So are you going from a wider to an, or
We went,
narrow?
Well,
we
we
went,
have the grading oriented this way, where the label is facing the laser, or should we have the label facing
I
the
don't care which
screen?
way, as long as you can tell me, is the slit getting wider or narrower?
the slit got narrower as we went to a larger, as we went to 0.16, the spacing got
All right.
smaller.
So you both have observed the same effect?
Yeah.
right? So that as the target, the source got narrower, the pattern got wider.
Right, yeah.
Okay? And there is a great, well, I'll come back to that one. All right, but this is a general feature of all of these phenomena. And you'll see on the, below the single slit diffraction, the formula that we learned in Physics 2. So we have for the single slit, we have our central maximum. And then a dark fringe, so this is our first dark fringe, M equals 1 dark. And there's also on the other side, M equals 1 dark. And over here we would have M equals 2 dark. And over here this would be M equals 2 dark fringe. If I draw the intensity on the screen as a function of the position X, I have our maximum coming down to the first dark fringe, and then it gets a little brighter after that and so forth. And so that formula describes the angle theta between the central maximum and where you would see any of these features. Okay? So for the single slit diffraction, the slit width W times the sine of the angle theta will locate the dark fringes for orders m equals 1, 2, 3, 4 by W sine theta equals m times the wavelength lambda. Okay? And again, you can go back to your Physics 2 text and look at the derivation for that, such as it is. So that locates the dark fringes. Now, if theta equals 90 degrees, that means this first dark fringe is way off to 90 degrees, which means the central maximum is entirely broad, covers the entire half space, or half of the half space anyway. And so that would happen so if theta is 90 degrees, sine of theta is 1. M equals 1, so W equals lambda. So when the slit width is equal to 1 wavelength, then our pattern is nearly isotropic. And then for any, if the slit width is any narrower than that, then the central maximum actually extends around behind the object. Okay, we get isotropic radiation. Okay, so radiation in all directions. So if the source is smaller than a wavelength, whether it's a single slit or if it's a trombone bell or a radio antenna or a light bulb or whatever, if the source is narrower than 1 wavelength, then the pattern is isotropic. Okay? Have you ever been to a football game where the marching band is marching around and they are marching towards you and you hear a very blurry sound and then they turn around? When you turn, you still hear them? Yeah, you still hear them, but it sounds very muffled, right? What you're getting is the low frequencies, long wavelengths, the wavelengths that are longer than the bell size. Now, in this case, the radiator is 2 dimensions rather than 1 dimension, and the criterion there is you get isotropic radiation if the wavelength is longer than the circumference of the bell, or whatever your circular radiator is. Okay? So long wavelengths radiate in all directions, isotropically. Then for shorter wavelengths, where the wavelength is shorter than the slit width, then our central maximum begins to narrow. So for example, if you go to a wider slit, then that's the equivalent to making the wavelength shorter than shorter. The ratio of the wavelength to slit width gets smaller in any case, and our central maximum narrows down. So again, for the trombones and the clarinets, well, clarinets is a different issue, but for trombones and trumpets, when they turn back towards you, the higher frequencies for which the wavelength is shorter than the circumference of the bell, now those radiate more directionally, and if they're pointing at you, the central maximum for those higher frequencies is pointing at you, and you hear that blaring sound. So the blare is the high frequencies coming at you. Okay? So I think this is one of the most important and most universally observed phenomena. We will see this every day of our lives, and now that you have thought about it, you will recognize it everywhere. Okay? And I encourage you to do that. So that's diffraction. Now, go to the other slide, which is the double slits. So take a look at the double slits first of all. And I've got more copies.
Oh wait, maybe it's this one.
If you just want to read what's written on them.
Just open your eyes. You will see.
So here's another copy of that if you want to just read what's on it.
Okay.
Here's another copy of the double slit if you want to read what's on it.
We got like 3 of them.
We have 4.
Okay, so take a look at this pattern. Do you see anything reminiscent of the single slit pattern in this?
Yeah.
Yeah,
There's none.
sure. And why would that be?
Why would what be?
So I asked the question, do you see anything reminiscent of the single slit pattern?
Yeah, in the center it's brightest.
Yeah, right. We have a double slit is 2 single slits, right? And so we start with that pattern. And then what's different?
Well, they're
Yeah, there we
messed
go.
it up.
There we go.
No, that was the wrong one. That was single slit. This is double slit.
Yeah. So
Bands.
superimposed on the single slit pattern, we see
Like
a bunch of little fringes.
Would this be
It's this thing right there.
a physical representation of 2 modes?
Of what?
Would this be a physical representation of 2 modes? Could it be? You know, this spacing of 2 slits representing a kind of oscillation?
Wow. So
There we go. You get close.
you're on the
It's
right
like a bunch of
track.
little-
In this case, we have 2 sources which are the same frequency. But at the end of the day, I want to talk a little bit about how we can get here from the Fourier transform. And in that sense, you're thinking along the right path. Okay, so which of the patterns in this sheet remind you of what you're seeing on the screen? Right, the one labeled double slit or double source interference. Okay. You will see here that the formula for this formula now, d sine theta equals m lambda distance between the 2 slits, and that this formula now refers to where the bright spots are, the bright fringes. D sine theta equals m lambda. Now, people start with, particularly in physics 2, start with the double source interference and talk about just this pattern because it's easier to think about just 2 sources. You'll notice that they're regularly spaced, right? Generally, as long as the, if I'm thinking about theta, these thetas are very small, right? Our pattern is really very, very narrow. But if we get down to, and that's because our separation between our sets is much, much, much greater than lambda. If we get down to separation being only a couple of factors of, say, 3 factors of lambda, then we would have only 3 maxima spread out in 90 degrees. There is a great video by Veritasium. You know the Veritasium? Yeah. There's, I just love this video. I would show it, but we don't have time. But I encourage you to go take a look. I'll put a link on for it. Among other things, they build a box, a big box, as a viewing chamber, and they put a little double slit in it so they can go out and look at. You can show it to people in the sun, right? So you go out to the beach and they have people look into the box because they can see the dark pattern.
Yeah.
And the sun, of course, is white light, so many wavelengths in it. And that's a great experiment right there. We also, one of the pedagogical tools that we use to describe the interference effects are wave tables where we have a little tray of water and we shine light through it and we make ripples on it, ripple tank. And those in the laboratory never work well. But he's got the best demonstration of ripple tank that he does by going out to a calm pond, and he's got two little balloons or balls that he's put on like 2 sticks, and he makes the 2 sources. And there it is. This is great. This is beautiful.
It is.
You don't get to see it.
So I encourage you to take a look at this video.
I'll flip it. Here, guys, relax.
Yeah.
Here you go. He's got 2 balls over here. He's moving.
All right.
And then look at that.
All right. I meant to bring and did not bring diffraction gratings. We have, hopefully, all of you have already gotten one of our diffraction gratings from one of our public events. If not, I was going to send out some more. Diffraction gratings are many, 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 many slits. So like the double slit, but just many of them. The diffraction pattern you can see, and I don't know, do I have any? Maybe I've got.
Moeller, that's his middle name.
If you look at the diffraction grading pattern, its bright spots are very narrow compared to the double slit pattern where the bright spots are wide and the dark fringes are narrow. In the diffraction grading where you have many, many slits, many sources, you get the same formula, d sine theta equals m lambda for the maxima, but the maxima are narrowed down. And so that's the distinguishing visual characteristic of the diffraction grading pattern compared to the double slit. In this case, they look like they're spread out simply because most diffraction gratings that we see have a very small spacing between the slits. We find diffraction gratings everywhere as well. If you've ever, CDs and DVDs, if you look at them, they have a sort of a rainbow pattern, and that's because there are many tracks on the CD, and those form, if you shine light on them, they form multiple equally spaced sources. Have you ever seen like an iridescent bird feather or an iridescent insect wing? Those are usually caused by, again, very regular ridges of some sort or other on the feather or the skeleton, exoskeleton. All right. So now what I want to do is calculate how to get these patterns. So I'm going to turn the lights back on. And so we will start with a two source and then we will build up. Because it's the same basic physics. So we'll talk it through and then we'll have you do it in code. So, what we have are two sources. So this is going to be two source interference, like double slit, for example. We have two sources that are some distance d away from each other. We have those sources radiated coherently, light with some wavelength lambda. Okay? And we need to make a choice of, we don't really care what lambda or d are, but we need to make a choice of how big d is compared to lambda. So let's make d greater than lambda, because we want to see this double source interference. So we'll pick a factor later when we get some of the numbers going. Then those sources are going to radiate. Eventually, they're going to fall on a screen. The screen is some distance L away. Okay. Now we could define it in terms of theta, but we're going to observe on the screen, and why don't we call this position, we'll call it y. So y equals 0 here, and then we will go out left and right from there. And we want to describe the waves that get on today. Okay, now, what radiates for light is the electromagnetic field. What radiates for sound is a pressure wave of some sort or other. And what we hear for sound, for example, is we hear the oscillating pressure, right? So whenever the pressure is large, we hear a loud sound. When the oscillations are, amplitude of oscillations are small, we hear very small sound. For electromagnetic waves, which you're looking at here, the electromagnetic field is radiating. The intensity that we will see, our eyes see intensity power, right? It's power that makes something bright. And so I'm not going to go through the E and M for this right now, but the power, or the irradiance in particular, is proportional to the electric field magnitude squared. Let's calculate, first of all, what happens to the electric field, and then we'll square it to get the brightness. So the electric field is radiating from here. And so it's going to be, I'll call it, this is electric field from call this slit 1, source 1, and call this source 2. And so this electric field is a traveling wave, and so I can express it as E, some constant, times, it's oscillating, so it could be a sine or a cosine or an exponential. All right, so let's use complex exponentials because we love those so much. All right, and so just as we saw on Wednesday, we could do e to the j omega t minus k r, where r is the distance that we've traveled. Okay, that make sense? And so this r, I'll call this r1. This r1 would be the distance from slit 1. And over here, we will have the same thing, E2 equals E0 e to the j omega t minus kr2, where r2 is the distance from slit 2. Okay. Now, we've been using e to the j omega t because we've been interested in time phenomena up until now. But now we're really interested in spatial phenomena. So we don't really care about the omega t part. It's there, and we can, when we calculate the magnitude is going to be E times its complex conjugate. And both of these share the same j omega t. So when I multiply by its complex conjugate, we'll have e to the j omega t times e to the minus j omega t, which will be just 1. So we are not going to care about that one at all, but we are going to care about the distance. And so let's flop this around. I get e to the minus j k r2 minus omega t, and e to the minus j k r1 minus omega t. All right? And instead of carrying this minus j up around all the time, we're now going to call it, wait for it, where did my markers go? Oops. Here's another marker. We're going to call this I. E to the I.
Oh my goodness.
We had to
All
wait
semester.
to the last day.
I told you
to
this
get
was
the iPad.
the acme of our semester, right?
Oh my.
All right, so E1 then is equal to E0 e to the j omega t times E, is it minus I omega t, e to the j, sorry, have it, e to the I k r1, okay? And E2 is E0 e to the minus I omega t, e to the I k r2, okay? And what we want to do is on the screen add up E total at a function of x, which is going to be E1 plus E2. Okay? And so that's pretty easy to do. that's gonna be, E0, e to the minus I omega t, which is gonna, that's gonna go away eventually, times, e to the I k r1 plus e to the I k r2. Okay? That make sense? All right, and that's easy enough. This is just going to be algebra at this point. So what's R1 and R2? Well, if I know the distance L to the screen, and I know my distance Y along the screen, and I know where my sources are, now I just have a triangle. Right? So R1 equals, how do I calculate the hypotenuse of my triangle?
Square root of L squared plus
Root of L squared plus
Y
Y
squared.
squared.
Or
plus Y squared, right? But my source is actually over this way a little bit. From the center point, it's over how much?
Half.
It's over d over 2, right? And so that's going to shorten that distance in the y direction. So it's going to be y minus d over 2 squared, right? And similarly, R2 will be what?
Y plus D over T.
Yeah,
Y plus d. All right, that's all we really need in order to do our calculations. So we'll have you go into Python now. We're going to have to define d and lambda and L and how far we want to go on y. And we're going to look along y as our screen, so we're going to need to create a bunch of y points. All right. Then we're going to need to calculate this e to the I k r1, so we can calculate these things and then sum them up, and then we need the magnitude of that sum squared. Okay, so let's make a list of things we have to do, and you can do this in your code as comments first. All right. So I'll work with you here. Oh, it's time we have. So pull up a new. Well, we could use the dimensions of what we have on our list right in front of you. So let's just do that. Pull up a. New Python window. File. New file. Let's call this Phy362 fall 23 double slit. I'm going to save it as that.
It's too small.
File. Save as. And then what am I going to say? I'll save it on OneDrive.
I could see you too.
2. Python. Okay, so physics 362, fall
But he's saving
23,
Yeah, he's just
double
saving his own.
slit.
We're all doing it from scratch, you know?
All right.
Scratch?
Where's that cat?
The first thing we're going to do, of course, is import libraries. Libraries.
You and my D wavelength L and E are all equal to 1.
What's the next thing we're going to do?
Define our
constant
veil.
value.
Define constants, right? So let's use the examples that we have in front of us.
What's our E?
Approximately, anyway. We need D, we need L, we need lambda, we need our Y range. So let's start with D. We're doing double slits. Off your screen, grab one of the D values.
0.5 millimeters.
0.5 millimeters, shall we go with that?
Slit space.
Okay. So, D equals, in meters, that'll be 0.005 meters, right? Meters. Slit separation. What else do we need?
Wavelength of light.
We need the wavelength. All right, what color light is this?
This is red.
It's red, so its wavelength is about
630.
650 nanometers or so. We'll call it 650 nanometers. All right, so that's 650 E minus 9. 50 nanometers, light, red light. Want to make sure that that will work. 650 E minus 9. Yeah, good. All right, what else do we need to define?
So
What other constants do we need?
What? No, but
Why? Okay, so y is going to be a bunch of points from left to right. So we need a y max and a y min, right?
That'd be like a.
So how big on your screen do you want to look? Something like that, so 20 centimeters,
Yeah.
That sounds
For
great.
real.
all right? So plus or minus 10 centimeters?
Why would I need-
So, y min is minus 10 centimeters.
Oh,
And y max will be plus 10 centimeters, right side. And we're going to need all the points in between, so we need a delta y. To get a nice smooth curve, we probably need 1,000 points, right? Roughly? I think 1,000 points will give us a nice smooth curve without being too gross. So, well, I'm just going to say n points because I just said that number is 1,000 number of points on screen. And so dy is going to be y max minus y min moin. Oh, shoot. Do that. Divided by n points. Okay? All right? Good so far? All right, what else do we need? We also need the distance
L.
L, right? So how far was that?
a meter. Say a meter.
What, a meter?
Yeah.
Give or take a little bit?
Yeah.
Meter?
Yeah.
Okay. So L equals 1 meter distance to screen. Anything else we need?
Do we need an initial,
What?
initial electric field value?
Sure,
or-
E0?
Yeah.
E0? How about 1? Now, one thing I left off of here, we may or may not wish to include it here. It'll be okay if we don't include it here, but to be more careful, we would have to allow for the fact that the electric field gets weaker. as we radiate outwards. So, this really should have some constant, divided by R in front of all this. Right? I'm just gonna I'll call R0, or L, maybe L, call it L over R1, multiplying the whole thing to make it weaker. Right? We don't need it for our calculation today, because we're not doing real numbers in, but if we're really concerned about it, we observe that the field is weaker out here. Okay? All right, any other constants that we need? So let's just go through the pseudocode. What do we need to do next?
Generate a Y list.
We need to set up the Y array, right? Set up the Y array. So that would be like an NumPy A range or something like that. All right. What else do we need to do?
Calculate R.
Calculate R1 and R2, right? Calculate R1, R2, which will be easy enough to do, because we can take the square root of the sum of the squares in NumPy very easily, right? Y is an array, L is a constant, but NumPy doesn't care. Or NumPy allows us not to care about that, it'll do it very easily. And then once we've done that, what do we do?
We make the E field functions.
What's that?
We generate the E field.
Yeah, generate the E fields. Generate the E fields. Once we do that, what do we do? After we've generated E1 and E2,
You add them together.
yeah, we sum them up, right? I can do that right now. E equals E1 plus E2, even though I haven't defined those yet. Plus. Okay,
Library?
what's next?
Libraries are
Oh.
Yes, there's no Y in
Oh, we
libraries.
That is why
square
it's
it.
called raries, right? there.
Yeah, find the magnitude of the square. Right?
This is it, is this it?
Yeah.
That's raw reads for your information.
You're the one that asked me how to spell
Not
libraries.
library. Well, it said it's spelled, it's not me, yeah, I never made
We lived in a
mistakes, so we're all
society.
just,
We lived in a society. Yeah. I'm only factual.
All right, and then after that, we can, what?
That means I don't care about your feelings because I'm only factual. No one is. I'm not that.
And that's it. Raise your hand if you think you know how to set up the Y array.
Oh, I got that, no problem.
Yes, sir.
Okay, that'll be using A range or something like that. Given the Y array, raise your hand if you think you know how to calculate R1 and R2.
Got it, done. Easy peasy, lemon
Okay.
squeezy.
You know how to sum the E fields?
Oh.
Adam?
no,
No?
Are we just gonna ignore the omega v squared and just care about?
The omegas?
Yeah, because the omega and t part, we don't care about that, right?
Yeah, because when we get down to here, those are gonna go away.
Yeah, so when we're making our E1 and E2, should we just have K and
Yeah,
R1?
right.
What we
You will not need the E to the I omega T.
won't we have to define K though, as well?
We will need to define K, yes. So that was, should be up in our constants. But we define the wavelength of light already. What is K then, the wavelength of light?
Okay, so
K is, K equals 2 pi over lambda. Right, so that would go up in your constants as well, I suppose. All right, well, we're way over time, so we should stop. But this will be your homework for chapter 8. And on the exam, the last exam, we will have you create the single slit version by simply, here we have 2 sources. The single slit version we can create by creating a bunch of sources. Right? And similarly, once you have that, you can also say, well, that looks an awful lot like a diffraction grating. And so you can use that same formula, but redefining what y's you're looking at and get the diffraction grating pattern. So those will be on the last exam. That plus a couple of problems looking backwards at earlier work. Okay, and I will post that by tonight, and it will be due by next Friday. And you are encouraged to participate in that, even if that's not going to be the exam score you want to. Even if that's going to be the exam score you're going to drop, I'll still give you extra credit for doing that. Okay, we good? You have fun this semester?
Yeah.
You know a lot of cool stuff? Yeah? Feel confident in using complex exponentials now?
Nope.
I don't know about that. That's
I got it, no problem.
And the stuff that we've learned here, we can use in lots of different ways. Jared and I were talking about maybe doing a 1-credit independent study course on op amps and filters. So if you want to think about electric circuit filters, you can, this is the same math we've been doing applies to that. So and anyone who's interested in that, let's talk about that between now and the beginning of next semester. Lots of different ways we can use this. Jared had asked the question, so if you don't mind, you're done, you can go if you want to. But because Jared asked the question, I'm just gonna go back. Ask something about normal modes, and I said, well, what's something we talk about in terms of Fourier transforms? So I'm just gonna go back to our Fourier transform documents. If I can find it.
Well, where's your answer?
your whole life.
What happened? Where did I go wrong?
That's the question for you guys. Maybe it was not monetizing your website. I think that was it.
I-K, nice, okay, yeah, then I add them together, okay, yeah, But you just look here. No, there's one.
And by the way, I've updated the document that's on Canvas. The one that was posted there was
Plus.
a somewhat incomplete version. And I've got a more complete version on there now.
I don't know why you switched it to E or switched it to I.
Just because.
But I have a bunch of examples.
I don't know.
So like you're free to go, as I said. But here's the first example. I have the, on the right-hand side, I have the Fourier spectrum, which is the frequencies. And on the left-hand side, I have the waveform. And so you can see the lower the frequency, the longer the wavelength, or the longer the period. So here I have two frequencies that are very close together. And over to the left, we have the waveform, which we can see has beats. But you can also think about this as a double slit. So think of these as a double slit in space, and the spatial frequencies, you can see, give us these, the peaks of the double slit pattern. Okay? The square pulse is like a single slit, and its Fourier transform gives you the single slit pattern that we see. Because it's just really the same. Here is a, you want to think of this as your diffraction grating. You get a very narrow peak in the transform value. Here again is our double slit, and we have the double slit pattern peaks coming up. So this sum that we do here, this is like the Fourier sum of these components. And so Jared's question, as usual, was right on the mark. And so, by the way, if you want to see a great hologram, you should take a look at Angelina's holograms. She's got a wonderful interferogram that
We're
just.
talking about my hologram.
Yeah. We are. We're talking about how good your
Great
hologram is.
holograms, guys.
You should see her hologram.
Okay.
She has a great hologram.
Oh, guys, they're so good.
Okay.
I ended up doing piezoelectric disc. I put 1 volt across it, exposed it half the time, no voltage, half the time with 1 volt across it. Guys, the best
Okay.
fringe.
Okay.
And I could see it when she was looking at it. I could see it across the room.